Welcome back to the deep dive. I want you to picture something for a second. You're talking to an AI on your phone. Maybe you're asking for a recipe or, just messing around. You ask a question, and then you wait. There's that little pause. And when it finally talks back, even if the voice is incredible, even if it sounds like a movie star, there's just something a little off.
It's the uncanny valley of timing.
Exactly. It feels like it's reading a script really, really well, but it's not actually speaking to you. It feels assembled.
That's because, fundamentally, it is assembled. And we've sort of hit a wall with how good we can make that sound using the current technology.
Right, and that's what we are unpacking today. We're diving into a research paper that claims we've been trying to cross that valley with, well, the wrong map entirely. We're looking at a framework called CAM that's continuous audio language models from the researchers at QTI.
And their big argument. We need to stop treating sound like it's text.
It sounds so simple when you say it like that. Sound isn't text.
But for the last few years, the entire AI industry has basically been forcing audio into a word processor. I mean, we've been treating Mozart and your voice memos like they're just paragraphs of text.
And apparently that's why our music generators take forever to render and why our voice assistants still need a massive server farm just to function.
Exactly.
So the mission today is to figure out how they're tossing out the vocabulary of sound and replacing it with, well, with physics, essentially.
Physics and continuous signals. It's a technical showdown. The old discrete way versus this new continuous way. And if these researchers are right, we're talking about high-fidelity, human-level audio running instantly on your laptop.
No cloud required.
No cloud required.
Which is a huge deal for anyone who cares about privacy or just, hates lag. But before we get to the solution, we have to understand the problem. You said we've been forcing sound into a word processor. Unpack that for us.
Okay.
When we use something like AudioLM or Musigen right now, what is actually happening under the hood?
So the current standard uses something called neural audio codecs. The specific term you'll see is RVQ, or residual vector quantization. Now, I know that sounds like a tax form.
It really does. It sounds like something I need to file by April 15th.
Stick with me. I promise it makes sense. Imagine you have a beautiful curving sound wave, a violin note, or a sigh. It's smooth. It's continuous. But computers, they hate continuous. They want nice, neat little boxes. They want ones and zeros.
They want a spreadsheet.
Exactly. So to make the computer happy, these models chop that smooth sound wave into tiny little slices. And for each slice, they look up the closest match in a codebook. Think of it like a dictionary of sound snippets.
Okay, so it's like a mosaic. You're trying to build a painting, but you're only allowed to use a specific set of colored tiles.
That is the perfect analogy.
Yeah.
And that set of tiles is your vocabulary. Now, here's where the RVQ, the residual part, comes in. If you just use one big tile, the audio sounds, well, blocky and low res.
Like an old 8-bit video game.
Right. Because you don't have a tile for violins playing specifically in D minor with a bit of reverb.
Yeah.
You just have a generic string sound tile.
Got it.
Precisely. So to fix that, they stack the tiles. They lay down a coarse tile for the general shape. Then they put a smaller, finer tile on top to add detail. Then an even smaller one for the texture. They build up a hierarchy of these codes to approximate the real sound.
So you're stacking layers of correction to get better resolution. That makes sense. But why is that a problem? It seems like a pretty clever workaround.
It is clever, but it creates what the researchers call the discrete bottleneck. If you want high fidelity, if you want that voice to sound like a real person in the room, you need a deep hierarchy. You need a lot of stacked tiles.
Okay.
And for an AI model to predict all those stacked tiles, it's exhausted.
It's too much heavy lifting.
It's a massive computational load because the tiles in a single frame depend on each other. Can't really do it all at once. You're stuck in this sequential tug of war.
You can have high quality or you can have speed.
But getting both, especially on a regular laptop, virtually impossible.
Now that's why running a high-end music generator on my phone is basically a pipe dream right now. I'm asking the phone to predict thousands of these words just to describe 1 second of sound.
Exactly. You're spending all your compute budget just managing this massive vocabulary of artificial blocks.
Enter CALM, continuous audio language models. I'm guessing the key word here is continuous.
It is. The team at QTI asked a pretty radical question. What if we delete the vocabulary? What if we just burn the dictionary?
Wait, if there's no vocabulary, how does the model know what to generate? It's not choosing from a list anymore.
No list. Instead of predicting a token ID like sound number 452, It predicts a raw, continuous vector.
Okay, help me visualize that.
Let's go back to your painting analogy.
Yeah.
The old way was the mosaic. You pick from a box of pre-colored tiles. The calm approach is like oil painting. You have a palette, and you can mix the colors. You aren't limited to blue number 4. You can slide smoothly between blue and green to get the exact infinite shade of teal you need.
That sounds infinitely more precise and also much more natural to how sound actually works. I mean, sound creates a curve, not a staircase.
Right. But there's a reason we did do this earlier. Computers, as we said, they love discrete categories. Making them predict continuous values, these floating point numbers, is mathematically much harder to control.
So how do they pull it off?
Well, first, they changed the architecture. They swapped out that tile-based quantization for a VAE, a variational autoencoder.
We've seen VAEs in image generation, right?
Yes. In this context, the VAE takes that audio and compresses it into what's called a latent space. But here's the key. It's not lossy in the same way the tiles are.
How so?
When you snap audio to a grid of tiles, you're basically rounding off the edges. You lose data. The VAE, on the other hand, preserves the smooth curves of the signal in a compressed mathematical form.
Okay, so we have a better way to represent the sound. We've got our oil paints instead of our tiles. But you still have to paint the picture. You still need a model to predict what comes next.
And that is where they hit a wall. In the early experiments, when they just tried to predict these continuous vectors, the model just fell apart.
Fell apart how? Like it just made noise.
It would start okay, but after about 10 or 15 seconds, the audio would lose all its detail. Or worse, it would just fade into silence.
Fade to silence. Why would it do that?
It's called error accumulation. Think of it like the game of telephone.
Oh, right. I whisper something to you, you whisper to the next person?
Exactly. In the old vocabulary models, you have a dictionary. If I whisper apple, you can guess I meant apple and correct it before passing it on. The dictionary keeps you on track.
But with continuous vectors, there's no dictionary to autocorrect from.
Right. So if the model is slightly off, say 0.1% off, that error gets passed to the next step. Then the next step is based on that error, so it gets 0.2% off. It compounds.
And eventually, it just loses the plot.
Completely. The model just gives up.
So they have higher quality paint, but a shaky hand. The picture gets blurrier the longer they paint.
That's a great way to put it. So they needed a way to stabilize the hand without going back to the, paint by numbers grid. And their solution was, honestly, it was kind of brilliant.
What'd they do?
They built a dual transformer architecture. 2 brains working in tandem.
2 brains. Okay, break this down for me. Who does what?
First, you have the causal backbone transformer. This is the big brain. Its job is to look at the long-term context, the big picture of the song or the sentence. It plans the structure. We're moving from a verse to a chorus, or we're finishing a sentence.
It's the architect.
Yes. But here's the clever part.
Oh.
During training, they intentionally sabotage it.
They sabotage their own model.
They inject noise into the audio input. They basically muddy up the signal so the big brain can't see the fine details.
That seems really counterintuitive. Why would you blind your architect?
To force it to stop micromanaging. If the input is noisy, the model can't rely on fine textures. It forces the backbone to learn the robust high-level structure, the rhythm, the melody arc, the grammar. It has to focus on the plan because the details are all fuzzy.
I see. If it can't see the texture, it has to focus on the shape. But we want the texture. I want to hear the grain in the voice.
And that is where the second brain comes in, the short context transformer. This is a smaller, lighter model. And crucially, it doesn't see the noisy version.
So it gets the clean version.
It gets to look at the most recent clean data.
Yeah.
Just the last 0.4 seconds or so.
Okay. So the big brain says, the blueprint says, we need a guitar strum here. And the little brain says, got it. And based on the last split second, that guitar string is vibrating exactly like this.
Perfect. The system synthesizes the noisy long-term plan with the clean short-term details. This stabilizes the generation. The short context transformer is constantly refreshing the texture, which stops that fade to silence issue.
Because it's always looking at a fresh, clean signal. That is really smart. It's like having a composer and a virtuoso player working together. One handles the sheet music, the other handles the instrument.
Exactly. And this dual transformer setup is really what makes the quality possible in a continuous space.
So we've solved the quality issue. We've got the dual transformers keeping things crisp. But at the top of the show, we promised speed. And honestly, dual transformers sounds like more work, not less. Does going continuous automatically make it faster?
Not automatically, no. In fact, if you're not careful, it can be slower. Previous attempts at continuous models, there was one called MAR used diffusion to generate the sound. And if you've ever used an image generator like Midjourney, you know about diffusion.
Yeah, you watch the little progress bar. It starts as static and then slowly clarifies into an image. Step 1, step 10, step 50. It takes a second.
Right. That iterative refinement is slow. For audio, a diffusion head might need hundreds of steps just to generate the next tiny piece of sound. That kills your real-time performance.
You're back to waiting. So what did Qt do? They didn't use diffusion.
They swapped it out for something called consistency models.
Consistency models. I've heard the buzzword, but how is it different from diffusion?
So think of diffusion as sculpting a statue out of marble. You chip away dust for hours, refining the shape bit by bit.
Okay.
Consistency models are trained to map the raw marble directly to the finished statue in a single step.
One step, from static to sound.
Ideally, yes.
Yeah.
Maybe a few more steps if you want extra precision, but the paper shows they can get high-quality results in just one shot.
That sounds like magic. How does that impact the speed numbers?
It's massive. Compared to the standard discrete models, the ones using that deep stack of tiles, this consistency approach reduces the inference time of the sampler head by a factor of 12 for speech.
Wow, 12 times.
And for music, up to 20 times faster.
20 times faster. That is the difference between waiting for a video to buffer and watching it live.
That's it. And this is why they call it a leap. It's not just an incremental improvement. It's changing the physics of how the sound is generated. You aren't decoding a massive stack of tokens. You just predict the vector and move on.
So we've got the VAE-JAN framework providing the continuous space, the dual transformers handling quality and structure, and the consistency models delivering the speed. It's a complete overhaul.
It is. But they also ran into some other interesting problems because they threw out the vocabulary. I saw you were looking at the notes on Gaussian temperature sampling.
Yeah, that caught my eye. We usually talk about temperature in AI as a creativity knob, right? High temperature means the model gets wacky. Low temperature, it plays it safe.
Right. In the Lego block models, temperature works by filtering out low probability words from the list. You basically tell the model, hey, don't pick any weird words.
But Calum doesn't have words. It doesn't have a list. So how do you tell a continuous curve to be less weird?
That was the puzzle. They had to reinvent the control knobs. Since they can't filter a list, they manipulate the Gaussian noise that is fed into the generation process. Specifically, they reduce the variance of that noise.
Reducing the variance, so keeping the randomness within a tighter range?
Exactly. By tightening that range, they achieve the same effect as lowering the temperature in a text model. It trades diversity for fidelity and stability.
So even without words, you can still tell a model to stick to the script.
Turns out you can. It's fascinating that they had to rebuild these basic tools from scratch just because they changed the underlying architecture.
It really highlights how different this continuous paradigm is.
It does. They also developed a training trick called the head batch multiplier.
Head batch multiplier. Sounds like a piece of industrial farming equipment.
It does, but it's an efficiency hack. Remember our big brain transformer, the one that plans the structure?
The architect.
Right. Running that architect during training is expensive. It takes a lot of energy to compute that long-term context. So instead of computing it once for one prediction, they compute it once and then reuse it multiple times.
Oh, I see.
They take that same context but apply different noise levels to the head of the model, the part generating the sound.
Ah, so they squeeze more juice out of the lemon, measure once, cut 3 times.
Exactly. They get multiple training signals from a single pass of the heavy backbone. It speeds up the learning process significantly.
Okay, so we have all these components. What does this actually look like in the wild? Because sometimes you read these papers and it's all theory. Did they actually build something with this?
They did. And this is the payoff. This is where it leaves the lab and, enters your life. They released a text-to-speech model called Pocket TTS.
Pocket TTS. The name implies small.
Very small. It has only 100 million parameters.
Okay, for context, when we talk about GPT-4 or the big models, we're talking trillions. Even small open source models usually have 7 or 8 billion parameters. 100 million is tiny.
It is microscopic. It's barely a blip. But because of this efficient architecture, because they aren't bogged down by that discrete bottleneck, it runs faster than real time on a standard laptop CPU.
A CPU.
They specifically mention running it on an Apple M3 and an Intel Core Ultra.
So no GPU. No massive graphics card heating up the room?
No cloud connection either.
Yeah.
Just the CPU in your laptop. And it's generating speech faster than you can listen to it.
That is huge. I mean, think about the implications. Right now, if I talk to Siri or Alexa, my voice goes to a server, gets processed, and comes back. That's a privacy risk, and it creates lag. This implies my device could talk back to me without my data ever leaving the room.
Precisely. Solves latency, it solves privacy, and it solves battery life. If you don't need to fire up a massive GPU or a Wi-Fi antenna to speak, you save a ton of power.
But does it sound good? Usually, tiny model means robotic voice.
That's the kicker. They compared it to baselines like F5 TTS. Pocket TTS outperformed them on word error rate, meaning it's more accurate, and on acoustic quality.
So it's smaller, faster, and better.
That is the promise of the continuous approach. By removing the discrete bottleneck, by stopping the process of chopping audio into inefficient tokens, you don't need a massive brain to manage the complexity.
Because the complexity was in the method, not the audio itself.
That is a really profound point. We were making it hard on ourselves by forcing audio to be text. When you let audio be audio, the math gets cleaner and the models can get smaller.
And I noticed they also tested this on music, not just speech.
They did, similar results. The column model with consistency was drastically faster than the baseline MusicGen models while achieving better FAD scores. That's fresh at audio distance, a standard metric for how real the audio sounds.
So let's zoom out for a minute. We've been living in a world of large language models, LLMs, and we've kind of just assumed that everything, images, video, audio, should be treated like a language model with tokens.
That has absolutely been the trend. Tokenize everything.
But Calm suggests that for continuous signals like sound, that might be a dead end, or at least a detour.
I think detour is the right word. Tokenization was a bridge. It allowed us to use the transformer architecture, which revolutionized text on other media. But now we're figuring out how to adapt the architecture to the media, rather than the other way around.
We're taking the training wheels off.
We are. And the implications for edge devices are massive. If you can run high-fidelity generative voice and music on a laptop CPU today, in 2 years, that's running on your smartwatch or your glasses.
That's a voice assistant that doesn't need to ping a server to figure out how to say hello.
Right. It makes the idea of conversational AI actually feel conversational. No pause, no lag, just fluid sound.
And nuances. Because we're in a continuous space, we aren't limited to a fixed vocabulary of emotional tones.
Exactly. The model can slide into very subtle inflections, a slight crack in the voice, a breath that might not even exist in a discrete codebook.
It's a fascinating shift. We've gone from chopping reality into Lego blocks to sculpting it out of clay.
And doing it at 20 times the speed.
Can't argue with that. It really seems like Qtai has laid down a gauntlet here for the rest of the audio AI field.
I think they have. I expect we'll see a lot more vocabulary-free models popping up in the near future.
Well, I, for one, am ready for my laptop to start singing to me without sounding like it's buffering.
Ideally.
Before we wrap up, I want to leave everyone with a thought. We spent this whole deep dive talking about how we're moving away from words and tokens to model sound.
Right.
If these models are now predicting continuous vectors physics, essentially, rather than symbolic tokens, are we approaching a point where AI doesn't just generate speech based on a database, but fundamentally imagines sound?
That is the question.
Is it mathematically closer to the way our vocal cords actually push air than it is to the way we write words on a page?
I think we're getting there. And that is a very exciting and slightly eerie place to be.
Something to think about the next time you ask your phone for the weather. That's it for this deep dive into call and the future of continuous audio. Thanks for listening.
See you in the next deep dive.